Here we're going to come up with the volume of a sphere using calculus. And if you can look at this picture and imagine that it is a circle that has volume in it. Let's say it's like a chocolate tennis ball, okay? A chocolate tennis ball. And we're going to take a slice out of this chocolate tennis ball, a thin slice. And that slice is going to be in a circular shape. And it's what we call our approximating disk. And once we see things about the disk, we'll be able to cut infinitely many little disks to form the entire sphere. Now, my picture is not very good. This is supposed to be a sphere of radius r centered at the origin. The x value starts at a equals negative r to b equals positive r. And the little slice is located x units out on the x-axis, and I've inscribed a right triangle there that shows that x is one side, y is the other, and the value r, which is a radius of this circular sphere, is the other. It's the point from the center out to the edge, and it completes the triangle. And also, we know that since it's a circular shape, it has the formula x squared plus y squared equals r squared. So if you solve that for y, it's the square root of x squared minus r squared minus x squared. Now, I think a better picture would be something like, say, this. In this picture, you can see clearly what's going on. I have taken in this picture a portion here of my chocolate sphere, my solid chocolate sphere, and I've cut a little slice out of it, and you can see the right triangle I'm talking about. It's r units on the hypotenuse, it's x units on the base, and it's y units up. So that's what I'm trying to show you there. Back to my crummy little drawing. We're going to show the volume of the sphere with radius r is equal to v equals 4/3 times pi times r to the third power. Okay, now first of all, the idea is to consider arbitrary disks that we've cut with tiny thickness, just infinitesimally tiny thickness, delta x. Then reconstruct the solid sphere by stacking these little disks together from x equals negative r to x equals r. In other words, from a to b on the x-axis. That's the idea, to reconstruct the chocolate tennis ball. So step one, we're going to find an expression for y. Well, the sketch, as we described earlier, shows that y would be the part of the equation for a circle. So it's y equals the square root of r squared minus x squared. We're only interested in the positive square root here because we're going to acquire this by spinning around the axis. And the limits, a equals the lower limit, negative r, b equals the upper limit r. The face of the area of the arbitrary disk, the face, would be found by, well, it might be a good idea to draw a picture of that face, the slice that we cut out in the original picture. We'll look at it straight on like this, and we see that it's the same. The y side is this y, and then the x side. Well, it does have an x side. So the area of that face is pi r squared, but r is y. It's actually y. So that's my bad. It wasn't x. X is how far it's coming out, but the actual disk is y radius. So it's y on both the upper leg and the left side. So y equals the square root of r squared minus x squared implies that we use that y for the radius. So a equals pi times r squared minus x squared. That's the result of squaring y. Okay, now we're going to find the volume. That's the integral from negative r to positive r of the area of the face, a of x dx. Volume equals negative r to positive r of pi times, well, what did we get for the area of the face? We got r squared minus x squared dx. Now we're going to use symmetry. Since we're integrating on a symmetric interval from negative r to r, we can say this is equal to 2 times the integral from 0 to r pi times r squared minus x squared dx. And then pi doesn't depend on x, so we can pull that out. and we get 2 pi on the outside, and then the antiderivative, pi squared x minus x cubed over 3. Evaluated from 0 to r. So do the evaluation at r minus the evaluation at 0. We get 2 pi times r squared cubed minus r cubed over 3. Okay, get a common denominator inside the bracket. We get 2 pi times 3r cubed minus r cubed over 3, which is 2 pi times 2r cubed over 3, which simplifies to 4/3 pi r cubed. And that is precisely the formula that we can find in any math book for the volume of a sphere of radius r. So we were able to come up with this strange way. This is a new idea to us. It's not really clear, but this is just an introduction to the idea of finding the volume of a solid where it involves a function that's actually, even though we didn't mention it, it's actually spun or revolved about an axis, which we'll see in the next several problems.